Good morning, students. Today we are going to discuss an important concept in semiconductor physics, that is carrier concentration in intrinsic semiconductors. This topic is very important for understanding how semiconductors work in electronic devices. First, let us understand what an intrinsic semiconductor is. An intrinsic semiconductor is a pure semiconductor that is without any impurity added to it. The best example is pure silicon or pure germanium. In an intrinsic semiconductor, the electrical conductivity changes only due to thermal excitation. At absolute zero temperature, it behaves like an insulator because no free charge carriers are available. Now, look at the silicon atom. Silicon has 4 valence electrons. Here each silicon atom shares its valence electron with neighboring atoms and forms covalent bonds. Because of these strong covalent bonds, at low temperature, electrons are not free to move. When the temperature increases, some electrons gain sufficient thermal energy. That is, these electrons move from the valence band to the conduction band. When electron leaves the valence band, it creates an empty space called a hole. So, in an intrinsic semiconductor, we get free electrons in the conduction band as well as holes in the valence band. So, these electrons and holes together are called charge carriers. Once the electrons are free, they move randomly inside the crystal and contribute to electrical conduction. Now, coming to the energy band diagram, you can see the valence band, conduction band, and Fermi-Newton energy gap, and the Fermi energy level. This is a Fermi energy level, and a conduction band, and valence band. In the absence of thermal field, in the valence band, almost all the electrons or valence electrons are completely filled and the conduction band is empty. So, in an intrinsic semiconductor, the Fermi energy level lies approximately in the middle of the band gap. So, here Eg is the band gap. This shows that number of electrons and holes are equal. That means electron concentration equal to hole concentration, and this is the key point we should remember. Now we are going for the definition of electron concentration, that is number of electrons present in the conduction band by unit volume of the material is called electron concentration. Hole concentration, number of holes present in the conduction band by unit volume of the material is called hole concentration. And carrier concentration, which is nothing but total number of charge carriers per unit volume of a semiconductor. So, in the case of intrinsic semiconductor, number of electrons equal to number of holes. Now, look at the diagram. Once the electrons are liberated from the bond, they become free electrons and move randomly through the crystal. See how the hole is created. Now we are going for our main topic, density of electrons in the conduction band. We are going to derive the number of electrons in the conduction band. So, the number of electrons per unit volume in the conduction band for energy between E and E plus D is given by dN equal to Z of E, F of E, dE. We know that Z of E, dE, which is nothing but density of states in the energy level between E and E plus dE, and we know what is F of E. F of E is Fermi distribution function. The definition of Fermi distribution function is it is the probability of an electron occupancy. So, the number of electrons in the conduction band for the entire range is calculated by integrating equation 1 between energy EC and infinity. Why? Because the minimum energy level for a conduction band is EC and the maximum energy level is infinity. So, we can write EC to integral EC to infinity dn equal to n equal to integral EC to infinity z of e f of e dE. Integral EC to infinity dn equal to n equal to integral EC to infinity z of e f of e dE. So here EC is the energy corresponding to the bottommost level, and infinity is the corresponding energy to the uppermost level in the conduction band. And we know the density of states in the conduction band between the energy range E and E plus dE. This topic is already calculated during electrical properties of materials equation. So Z of E dE equal to 4 by h cube into 2m whole power 3 by 2 into e power of dE. So here the bottommost edge of the conduction band EC denotes the potential energy of the electron at rest, which means here EC is the minimum energy level and capital E is the maximum energy level. So we can replace capital E as E minus EC in the equation number 3. So now look at the equation number 4. Here equation number 4 is Z of E dE equal to 4 by h cube into 2m E star whole power 3 by 2 E minus EC whole power half into dE. Here m is replaced as m star, which is nothing but effective mass of an electron. Small m we can call it as rest mass of an electron. M E star is effective mass of an electron. So the mass difference is there. So these electrons in the conduction band are not totally free. They move in a periodic potential of the crystal lattice. Therefore, in equation 3, the mass of the electron is replaced by effective mass according to the band theory of solids. So now we know what is Fermi distribution function. Fermi distribution function, which is nothing but probability of an electron occupation, and the value is 1 by 1 plus exponential of E minus EF by kBt. Right, and now we are going to substitute equation 4 and equation 5 in equation number 2. We know that what is equation number 2. That is equation number 2 is integral EC to infinity Z of E f of E dE. So instead of Z of E value, we have to substitute this 4 by h cube and 2m E star whole power 3 by 2, and we know E is replaced as E minus EC energy level, so E minus EC whole power of, and instead of f of E we have to substitute the value 1 by 1 plus exponential of E minus EF by kBt into dE. Right, so we have substituted the equations equation 4 and 5 in equation number 2, and further simplification we are going to take this 4 by h cube into 2m E star whole power 3 by 2 into outside of the integral, so that we can write it here, and remaining integral EC to infinity, so E minus EC whole power of divided by 1 plus exponential of E minus EF by kBt into dE. So again I'm going to include E minus EC whole power of into inside the integral, the only change. So here kBt or kT, the value is very small, so that E minus EF by kBt is very much greater than kBt, because if kBt is value is very small, then automatically we can conclude that E minus EF is greater value, so that exponential of E minus EF by kBt is very larger value compared to 1. So hence 1 from the denominator of the equation number 6 is neglected. So now we are going to neglect the value of 1 in the denominator of equation number 6. That is 1 plus exponential of E minus EF by kBt is approximately equal to E minus EF by kBt. So now equation 6 becomes, now we are going to eliminate this only 1, right? So we can rewrite this equation number 6, that is n equal to 4 by h cube into 2m E star whole power 3 by 2 integral EC to infinity, and the remaining value we know that E minus here E minus EC whole power half into exponential of E minus EF by kBt into t. But look at here we are introducing minus E minus EF by kBt because it is denominator. When it goes to numerator, we can put a negative sign here. So now equation 6 becomes n equal to 4 pi by h cube into 2m e star whole power 3 by 2 integral ec to infinity. So e minus ec whole power of into exponential of minus e minus ef by kBt into dE. So now we are going to rewrite the exponential term. That is, now we are going to split the term. In the exponential term, we are going to split this exponential term into two. That is, exponential of ef by kBt is one term, another one term is exponential of minus e by kBt. So we are going to split this term. Now we are going to substitute this splitted terms in the equation number 6 so that we can get n equal to 4 pi by h cube into 2m e star whole power 3 by 2 into exponential of ef by kBt. So now we are going to take this exponential of ef by kBt into outside the integral. So that is why we have right here, and the remaining is integral ec to infinity. As usual, e minus ec whole power of is here, and exponential of minus e by kBt into dE. So that is our equation number 7. Now our ultimate aim is to evaluate the integral. For that I am going to assume some terms, that is e minus ec as x. So if you want to solve the integral in the equation number 7, you have to assume e minus ec term as x, right? So now take it this term into left hand side, so we can write e equal to ec plus dx. So differentiate this dE with respect to x, so dE equal to dx, so constant term eliminated. Now we are going to apply the limit. When e equal to ec, then we can say x equal to 0. When e equal to infinity, then x equal to infinity. So now we need to substitute all this x value, e value, dE value, and x equal to 0 and x equal to infinity. All these values we have to substitute in equation number 7. Alright. So n equal to 4 pi by h cube into 2m e star whole power 3 by 2 and exponential of ef by kBt. There is no change at all. You just keep it here, right? So instead of ec, you have to substitute the lower integral as 0, right? The upper integral is infinity, right? So remaining, you have to substitute the value e minus ec. Instead of e minus ec, you have to put it as x, and we know exponential of minus e by kBt. So instead of e, we have to put ec plus x, alright? Look at here, instead of e, right, we have to write e plus x. So remaining k by t is kBt, and instead of dE, we have to write dx here. Okay. Now, so we have substituted all the values in the equation number 7. Now, take out the constant exponential term, that is exponential of minus ec plus x by kBt. Now again we have to split this exponential into two terms. One is exponential of minus ec by kBt, another one term is e power minus x by kBt. We can say like that. So n equal to 4 pi by h cube into 2m e star whole power 3 by 2 into exponential of, already we have ef in the outside the integral. Now we have to take this exponential of minus ec into outside the integral, so that we can write exponential of ef minus ec by kBt. So remaining integral 0 to infinity, and we know x power of is there, and exponential of minus x by kBt into dx is there. So that is our equation number 8. So now we using the gamma function, we know it is shown that integral 0 to infinity x power of exponential of minus x by kBt into dx, the final answer or the final solution for this integral is kBt power 3 by 2 pi power 1 by 2 divided by 2. So here in the equation number 8, instead of this 0 to infinity x power of exponential of minus x by kBt into dx, we have to substitute the value kBt power 3 by 2 into pi power of divided by 2. So that is substitute equation 9 into equation number 8. It's a very simple step. Just replace the term and we can write n equal to 4 by h cube 2m e star whole power 3 by 2, second term, third term, exponential of Vf minus Ec by kBt, it is already there. So instead of that integral value, we just replace kBt whole power 3 by 2 and pi power 1 by 2 or root pi divided the whole divided by 2. So rearranging the final expression, we can write the number of electrons or density of electrons in the conduction band, that is n equal to 2 into 2 pi m e star kBt by h squared whole power 3 by 2 into exponential of minus Ec minus Ef by kBt. And thank you so much, and in our next class we are going to discuss about density of holes in the valence band. Thank you.